Hi friends, welcome back to our series of Control Systems Simplified. Today we'll discuss about block diagram algebra related to control systems. The basic elements of a block diagram are a block, the summing point, and the takeoff point. If you consider the block diagram of a closed loop control system, which has a transfer function of G of S and H of S, it also having one summing point and one takeoff point. Arrows indicate the direction of the flow of signal. Now let's consider individually, this is a block. The transfer function of a component is represented by a block which has a single input and single output. The following figure shows a block having an input X of S and an output of Y of S, the transfer function G of S. That's how we are seeing. So the transfer function is G of S is equal to Y of S divided by X of S, or the output Y of S is nothing but G of S into X of S. So we can say that the output of the block is obtained by multiplying the transfer function of the block with the input signal. Then we have the summing point, which is represented with a circle having a cross inside it, which has two or more inputs and a single output. It produces the algebraic sum of the inputs and also performs the summation or subtraction or combination of summation and subtraction of the inputs based on the polarity of the inputs. So if you see one by one, so this particular figure shows the summing point of two inputs A and B, which gives Y as summing point A plus B. Now this figure here, we will see some input A and input B, whereas we have A as a positive sign and B a negative sign. So the summing point at output Y is equal to A minus B. Then here we will see we have three signals, A plus B minus C. So similarly, we will get the output is equal to Y is equal to A plus B minus C. Then we have a takeoff point here, which is a point from which the same output, same input signal can be passed through more than one branch. That means with the help of a takeoff point, we can apply the same input to one or more blocks or summing points. So here the takeoff point is connected to the same input R of S to two or more blocks. So GA of S, GB of S, or GC of S. Then again, we have one more thing which a takeoff point is used to connect the output C of S as one of the inputs to the summing point. Now, we also have the electrical signals to represent with a block diagram. Electrical systems contain mostly RLC, the resistance, inductance, and capacitance. In this RLC circuit, we have Vi of t input and V naught of t as the output signal. Now in this circuit, by applying we have a time domain circuit. I of t is the current passing through the circuit, and this circuit is in the time domain. So by applying the Laplace transform to this circuit, we'll get the circuit in S domain, which is same the current. Vi of S is the input, V naught of S is the output. And then if we apply Laplace transform to R, we get R. And then to Li, we get SL. And then 1 by SC here. So from the above our circuit, we can always write I of S is equal to Vi of S minus V naught of S by R plus SL. So implies IS is equal to 1 by R plus SL into Vi of S minus V naught of S. So whereas V naught of S is again equal to 1 by SC into I of S. That's the current that is flowing through the signal. Now these block diagrams, two equations, if we see individually, then they combine those block diagrams properly in order to get the overall block diagram of the RLC circuit in S domain. Now this equation can be implemented by having a transfer function of 1 by R plus SL. This is the transfer function. The input and output of this block are Vi of S minus V naught of S. So V naught of S is coming from this side, Vi of S, this has a negative feedback. So Vi of S minus V naught of S is the input and I of S is the output. Now the same thing, this can be, next equation can be represented with a block diagram having a transfer function of 1 by SC, whereas I of S as the input and V naught of S as the output. Now the overall block diagram of the RLC circuit in S domain is shown here with Vi of S and V naught of S, where we are getting this feedback as V naught of S here, and that's giving Vi of S minus V naught of S. So we are adding two blocks here, 1 by R plus SL is one gain, and the resulting is I of S, and then I of S is input to the 1 by SC, that's what we are giving here, then we are getting the V naught of S. So similarly, we can draw the block diagram of any electrical circuit or system just by converting, this is the procedure that is followed by converting the time domain electrical circuit into an S domain electrical circuit by applying Laplace transform. Write down the equations for the current passing through all the series branch elements and voltage across all shunt branches. Then draw the block diagram for all these equations individually. That is also equally important. And then combine all these block diagrams properly to get the overall block diagram of the electrical circuit in the S domain. That's what exactly we have done here. This is the procedure to follow to draw the block diagram of any electrical circuit. Hope that is clear. Then we will see the block diagram algebra is nothing but the algebra involved in basic elements of the block diagram, okay, which represents in the pictorial representation. So basic connections of the blocks are series connection and parallel connection. Here we see the series connection where G1 of S is connected in series to G2 of S. And this is represented. So Y of S is given G2 of S into Z of S, where Z of S is nothing but the G1 of S of X of S. So in the result, Y of S is equal to G2 of S into X of S. So the combination here, the combined block diagram, we can write always for the X of S is equal to G1 of S into G2 of S. So the result Y of S is given as G2 of S. If you take it common, G1 of S into X of S, whereas this, if you remove this, G1 of S into G2 of S into X of S. So we can always say that G1 of Y of S is equal to G1 of S into G2 of S as the gain times the X of S as the input. Right? So that means we can represent the series connection of two blocks with a single block, and that is the product of the transfer function. If you see the parallel connection, the blocks which are connected in parallel, G1 of S and G2 of S, are connected in parallel here. And here we have Y1 of S and Y2 of S are given to the summing point. This. So Y of S is equal to Y1 of S plus Y2 of S. Whereas Y1 of S is nothing but G1 of S into X of S. Whereas Y2 of S is nothing but G2 of S into X of S. Okay. So the result Y of S will be G1 of S plus G2 of S into X of S. That is the, so the sum of the transfer function, if you connect these blocks in parallel, so the total transfer function is nothing but the sum of the individual blocks transfer function. Then we have the feedback transfer function. So feedback transfer function here, we have a positive feedback and negative feedback. The following figure shows the negative feedback control system here. The output of the summing point E of S here is equal to X of S minus X of S into Y of S, whereas the output Y of S is Y of S, G of S into E of S. Okay, so if we substitute E of S is X of S minus X of S into Y of S, and this is what we get finally, and we get the Y of S is equal to X of S minus X of S, H of S into Y of S into G of S. If we remove this bracket, then we will get Y of S by X of S is equal to G of S divided by 1 plus G of S into H of S. This is a very simple transfer function for this, which we can do it very easily. So this is for the negative feedback. So if you take the positive feedback, we will get Y of S by X of S is nothing but G of S by 1 minus G of S into X of S. That's the basic difference. For a negative feedback, we get 1 plus G of S into H of S, whereas for a positive feedback, we get 1 minus G of S into X of S. Then we have a block diagram algebra for summing points, shifting summing points after the block and before the block. So that these are the two conditions here. If you see the shifting of the summing point after the block, now the summing point is before this block, G of S. And here, after this summing point, we have R of S plus X of S. Okay, so the input to the block G of S is given by R of S plus X of S. So the result, Y of S is nothing but G of S multiplied by R of S plus X of S. Now let's see what happens if we shift the summing point after the block. You will notice here, the summing point before it was here, now it is after this block, summing point after the block. So the output of here is G of S into R of S. And here we are getting G of S into X of S. So the effect Y of S is equal to G of S into R of S plus X of S. Because G of S, the output of this summing point is nothing but G of S into R of S into X of S. So that's the summing point. Now shifting the point before the block, if you want to see, now here the summing point is after this. Okay, so output of this block diagram is Y of S is equal to G of S into R of S plus X of S. This is what here we are getting for Y of S. Okay, now the output of this block diagram, if we shift the summing point to before this block somewhere here, this is exactly what we are doing. Now shift the summing point here, we are getting 1 by G of S into X of S. So after the summing point, we are getting R of S plus 1 by G of S into X of S multiplied by G of S. And that's what exactly is the Y of S. Okay, so Y of S is nothing but G of S into R of S plus G of S into X of S. Now, we have the same case for the takeoff point, where shifting the takeoff point after the block, right? Shifting the takeoff point after the block, if we consider. Similarly, we have for takeoff points also shifting takeoff points after the block and shifting takeoff points before the block. Okay. Now, if you see the takeoff point after this is exactly what we have. Before this, we have the block takeoff point. Now we are shifting this to after this. So we get X of S is equal to R of S and Y of S is equal to G of S into R of S. Okay. So when you shift the takeoff point after the block, the output Y of S will be the same, but there is a difference in X of S value. So in order to get the same X of S value, we require one more block as 1 by G of S. This is important. It is having an input of Y of S and the output is X of S. Okay, so this is how we represent that block diagram. Then shifting the takeoff point before the block. Now here, the takeoff point is after the block, which has X of S is equal to Y of S, that is equal to G of S into R of S. Now, if we shift the takeoff point before the block, the output Y of S will be the same, but there is a difference in X of S value. So in order to get the same X of S value, we require one more block G of S, which is having an input R of S and output is X of S. Okay, thus the block diagram is shown like this. This is exactly what we have for so then we will see the block diagram reduction rules, which basically are in this formula. We have to follow 6 rules. Let's see one by one. Block diagram reduction rules is rule number 1, the blocks. Check for the blocks connected in series and simplify. Rule number 2, Check for the blocks connected in parallel and simplify. Rule number 3, check for the blocks connected in feedback loop and simplify. Rule number 4, difficult. If there is difficulty with takeoff point while simplifying, shift it towards right. If there is a difficulty with summing point while simplifying, shift it towards left. And repeat the above steps till you get the simplified form, that is the single block. Okay, so the transfer function present in this block is the transfer function of the overall block diagram. Now here in this block diagram, let's use, we are taking this as an example, a block diagram which has all these things. Okay, now if we use rule number 1 for block G1 and G2, we have G1 and G2 mixed here. Similarly, G3 plus G4, which are parallel, are connected here for this. And then step 2, we are using rule 3 for blocks G1, G2 and H1. Use rule 4 for shifting takeoff point after G5. So the modified block diagram is given as G1, G2 by 1 plus G1, G2 into H1. And here G3 plus G4 to G5. Okay, so that is exactly what we are getting. So in step 3, use rule 1 for blocks G1 for G3 plus G4. So we get and G5. So we get G3 plus G4 into G5. The modified block diagram looks like this. So in step 4, use rule 3 for blocks G3 plus G4 into G5 and H3. Okay, then we are combining the feedback here. The modified block diagram looks like this. Step 5, use rule 1 for blocks connected in series. So we are getting the total one. So we are getting G1, G2, G5 into G3 plus G4 by 1 plus G1, G2 into H1 to 1 plus G3 plus G4 into G3, H3. Still H2, 5 is in parallel. Now we use rule 3 for blocks connected in feedback loop. This is connected in order to get a single block. And if we use rule 3 for blocks connected in feedback loop, the modified block diagram is shown in the following figure. And this is the simplified block diagram. So follow these steps in order to calculate the transfer function of the blocks. Block diagram having multiple inputs. So step 1 is find the transfer function of the block diagram by considering one input at a time and make the remaining inputs as 0. Step 2 is repeat step 1 for remaining inputs. And step 3 is get the overall transfer function by adding all those transfer functions. So the block diagram reduction process takes more time for complicated systems because we have to draw a partially simplified block diagram after each step. So in order to overcome this block, we have a signal flow graphs that we will see it in our next video. So thank you very much, and want to watch more related video, please subscribe the channel.